Hello, pre-calculus student. This video is for chapter 4.4 and 4.5, log graphs and log properties. In 4.3, we introduce log function, log base b of x. This b is a name for log, so it has nothing to do with interfering with x. So x is the input to the log function, and the answer for a log function is the exponent. So, and it is the inverse of an exponential function of b to the x. For example, if I have a f of x equal to log base 3, then the corresponding inverse function is f inverse. They are inverse of each other. So this is the base 3, so it would be 3 to the x. That means when I have a 1, I use this 3 to the x will get me 3. If I have 2, with 3 to the x would get 9. When I have input -1, the 3 to the x will give me 3 to the -1, which is 1/3, right? So this is the exponential function. The log function would be the other way around. If I have 3, because they're inverse of each other, if I have 3 input, log base 3, I would the 3 would map me back to 1. So 3 as the output of the exponential, it is come from 1. So this would map 3 back to 1. And if I have 9, I go through the log function, log base 3 function, it will give me 2. If I have 1/3, log 3 1/3, then the log 3 function will map me back to -1. So you can see that x, y, and yx are the same for the log function and exponential function because they're inverse of each other. And because of that, so if I have x, I go to log base b to y. It would be the same as 3 to the y will get back to x, right? So if that is the case, the domain of the log function is equal to the range of the exponential function. So you can see the domain of the log function 3, 9, 12 in this example was the range, right? So they are just reverse of each other, inverse. So our first skill that we need to cover is what is the domain of the log function then? Like if I ask, oh, what are the allowable input in the log function? In this example that you have, you can see that, well, I have 3, 9, 1/3. All of these log function input are positive number because they come from the range of the exponential function. And we know for the exponential function graph, the graph is like this, right? For the gain function, no, not this one. The 3 to the x is a growth function. So it is always, we're exclusively graphing like that, right? We're exclusively graphing on the top of the x-axis. So it's all positive y. So it is reason to believe that the domain of the log function will be all positive x. So we say since the range of y equal to b to the x exponential function is from 0 to infinity, so domain of the log function is also 0 to infinity, because this is the key idea is domain and range of log and exponential kind of swap. So if someone asks me to find domain of a general log function, not just log base 3 log base b to the x, but more complicated a log base b and then something x plus something and then outside plus something. What is actually the domain? So because I know the simple one, log base bx is inverse with b to the x, right? These two are inverse. But if I have a whole bunch of stuff and then multiply and then add something, would the inverse be different? Would the domain be different? So it turns out that we do it this way. The how-to is you set up an inequality to make sure that everything inside here, log of something, has to be positive because log of anything is positive. So it could be kx plus c, but this result, we call this the argument. Okay, so this is a technical term in math. Argument means the input inside a function, or the input inside function, including algebraic combination. And then you solve for x and write in interval notation. So that would be the domain. For example, find domain of a log function which is more complicated than log base 5x, but log base 5x plus 5. It could be x plus 2, it could be x plus 3, something like that. Then we say the argument is all the things that is inside the log expression. So it's x plus 5. And then for finding domain, that's what has happened is we always write an equation, write an inequality or equation to solve. To find domain, we solve an inequality that you write is x plus 5. This argument has to be positive because in general, all log functions are positive. Function input are positive. And then you divide your minus 5 and solve for this inequality. That means your actual real x input has to be greater than negative 5. So in the number line, it would be negative 5. Everything greater than negative 5 is here. Then you say, okay, it's negative 5 to infinity is the domain. It's a domain of what? The original log function that you have. Okay. If this is no add or something, it would be just greater than 0, 0 infinity, like here, if just x. But if you have something else in the argument, then you have to solve an inequality. So that's the basic idea. Example B, 1b would be, I have a log base 3, negative 2x plus 4. So what is the argument? The argument is negative 2x plus 4. In order to find the domain, I have to solve an inequality of negative 2x plus 4 greater than 0 because all input has to be greater than 0. Negative 2x, so I do minus 4, negative 2x minus 4. This is a 0, negative 4, right? And then I divide by negative 2, divide by negative 2. Oh, when I'm dividing negative for inequality, I have to switch. And negative is positive. So it turns out that for this particular log function, x has to be less than 2. So I'm going to draw 2. This symbol is a less than. And the interval notation is negative infinity to 2 is the domain. Remember, our goal is not to solve the inequality. Our goal is find a domain, but we use inequality to figure out the domain. The idea is log of anything has to be positive. So this is how you do. When someone asks you find domain of a log function, is positive. Just set out inequality of x plus 5 greater than 0. So now we're switching to understanding this, then we would ready to graph a log function. So I'm going to do it in the second video. So this is watch the second one on how to graph the log function. The domain is a setup. So that means when we pick points for x, it has to be all positive number.